for us. So we can ask now, what's the probability that a certain bit value will make my check equation, my check node, be 0. So this is why we actually need this kind of probability, what we will see right away. Okay, then we came back to our example, this 7,4 Hamming code, and trying to understand what is going on here. So I picked one example here. For example, we want to get additional information on our bit node 3, so the third received value in our code word, for example. And the task of the decoding stage is now try to extract as much information from the other bits as possible. What can we learn from these other observations about our bit 3? If we can learn something, we can get some information on bit 3 because somehow the bits are linked over our parity check equations. So obviously this green bits here, these green observations somehow meet at check node 2, and we know in order to be a valid code word, we need to get a 0 here at check node 2. So for example, we came up with some example with numbers here. If with probability 0.9, the second bit, the second observation is a 1 bit, with probability 0.8, this observation is a 1 bit, and with probability 0.9, this is a 1 bit. So all three very likely to be a 1. So notice in this case, the sum of these three green guys up there will also be probably a 1. 1 likely from here, 1 likely from here, 1 likely from here. Sum of the three green guys, a 1. And from this, we can conclude something on this red guy we are interested in. If the sum of the three green guys is likely to be a 1, then the red guy must likely be a 1. Because in this case, we would get a 1 plus the 1 from the green guys, and our parity check would be fulfilled. 0 at the check node, everything fine. So this means from the probability of the other bits, we can get a probability for the desired bit here to be a 1 or to be a 0, whatever we are interested in. And this is the so-called extrinsic information. So we get information on the desired observation, on the desired bit, which does not come from the observation of this actual bit. It comes from the observation of the other bits. External, extrinsic information. So independent information on this bit. This is the most important thing to understand here. We extract information from the other observations on the bit that we are interested in. And if you just imagine the probabilities, this is straightforward that this must work somehow. And here we just described it in some words and equations. But most important is the principle. Yes, then we wrote this in a more formal way. How exactly we needed this equation. So what's the probability, for example, that the sum of these three green guys turns out to be a 1? And this will actually give us the probability that the red guy needs to be a 1. So in our example with the numbers, we can conclude with this given probabilities, with 88.4% probability, the red guy must be a 1, because then our parity check would be fulfilled. This is actually what we can use this kind of equation for. This is this extrinsic probability, the extrinsic information that we can extract over parity check node, over check node 2 for our information bit 3. Okay, and we need to consider basically all information bits that are linked to check node 2. This is this union B2. So all out of this one, just not the one we are looking at. So for example, we do not consider the value from the third guy going up here. Well, because then we would actually include already intrinsic information in our calculation. So we would reuse the information from the observation here. But this is not what we are interested in. We are interested in the independent information that we can gain from this step in the process. So just not the one we are interested in, and actually this turns out to be this value. Yes. Yes. Let me just repeat the question briefly for the audience, for the online participants. So here the question was what the index 2 is referring here. It's referring to the check node. So we will get some more extrinsic information on our observation, on our information bit 3. We will also get some E13. So we can also get extrinsic information using check node 1, then using check node 2, and using check node 3. So we get actually at the end 3 probabilities. So what probability can we conclude from check node 1 for information node 3, from check node 2, and from check node 3? I will explain this again when we look at the example on the lecture slides, because there I calculated all these 3 values. But here, for the explanation, I just used one case, namely the case, what can we gain over check node 2 on our bit node 3? Okay. So then, basically, from the understanding point of view, this is clear. Just in practical systems, it's done slightly different. So far, we talked about probabilities. This is maybe more easy to imagine, more easy to understand. In the next step, we move again from probabilities to log likelihood ratios, which just makes the equations a bit more difficult. But you see, instead of talking about these probabilities here, we can also talk about log likelihood ratios, just setting these probabilities in relationship and using the ln. So and in this case, instead of the probability, we will get a log likelihood ratio. Just putting in the equations and simplifying stuff brought us to this, well, not really easy looking equation, but that's how it's typically done. Using here, maybe you wondered about this relationship, but this is actually from like a math book equation that we can use here, a relationship between the hyperbolic tangent and the ln, how this can be simplified. Okay. So then in the next step, we need to bring the information together. So we have several check nodes where we get extrinsic information on our bit node, and we have the a priori information from the observation of our. This has so far not been considered because we were just talking about the extrinsic information, what can we get from the other bits. But of course, we have also some information from observing this value. Maybe it's minus 0.3 or plus 1.2. Also here we have some information. And at the end, of course, this needs to be brought together, the extrinsic information from the other bits and the intrinsic information from the observation of our bit. This will be finally the log likelihood ratio of our bit node of our observation number 3 here in this case. Okay, and this is actually where we want to start today. But actually, before we start here, I want to come back to one of your questions and then using the lecture slides, explaining you some stuff. But let's come first to our question. So we are the student asking for good student question. LLR for non-binary case. So actually, I had a look at this, I think 2 or 3 years ago. I had a student like working on non-binary LDPC codes. This is why I already got in contact with this and tell you something about this. So far, you had like a binary modulation scheme, for example. So you have 1, -1, or the corresponding mapping. This would be the 1 bit, this would be the 0 bit. And we basically define the log likelihood ratio as the ln of the probability of, let's say, a received value y to be +1 divided by the probability of y here -1. It's just a ratio of probabilities, these log likelihood ratios. We can calculate these probabilities if we know the distribution of the noise, for example, additive white Gaussian noise channel. We can come up with this, so it's not really difficult. So we could also say, different expression here, we could say, okay, we use this probability y to be -1 as reference. Let's say, so do it like this. AI, if we map it to bit values, we map the +1 to 0 bit or -1, 1 bit. Well, it's equivalent in terms of the probability. It's just mapped to some different values. Now, non-binary. Example, imagine such a constellation like a QPSK or QAM, however you want to call it. And we could, well, actually there's not even a need to assign bit values to these guys now. We could also say this is like symbol 0, symbol 1, symbol 2, symbol 3. Non-binary symbols. And also here I would have decide for one to be the reference. Choose one reference. For example, I could choose the 0 symbol. Then I can basically define or calculate some more likelihoods. For example, I could calculate L1 being the ln of y being 1 divided by our reference p of y being 0. We will get a L2 p of y being 2 divided by our reference. And we get a L3. Well, it's straightforward. So the last guy, p of y being 3 divided by our here, p of y being 0. So this means at the end, we will get a vector of log likelihood ratios. And now do you have an idea? What do we do with this vector of log likelihood ratios? How could I come up with a decision when looking at this vector? I mean, here it was easy. I get just one value. Just look at the sign. But what do we do here in this case? How do we come to our decision? Sorry, I didn't understand. It's easier when we come up with an example. So let's assume we have an observation. Let's say this guy here, which is fairly close to value 2 here. We could also introduce some Euclidean distances here. So already from looking at the Euclidean distances, you could tell most likely symbol 2 was transmitted. But what does this mean now in terms of our log likelihood ratios? So e.g., so I just put in arbitrary numbers now. So the probability that the observation is more likely to be a 1 or a minus or a 0, you see 1 is slightly more likely as 0, so this would be a fairly small positive value. Maybe let's say 1 point. And the L2, it's the probability that it is a 2 as compared to a 0. 2 is way more likely as 0, so it would be a larger value, be 5.3. And finally, the last one, the probability that symbol 3 was transmitted as compared to number 2, well, it's somewhere in between. So maybe like 2.3. Exactly, yes. Yes, let me repeat the question again. So here in the audience, the question was, the more further away a symbol is from our observation, the more unlikely it is. Yes, and this is true due to the fact that we have Gaussian distributed noise. In this Gaussian distribution, the probability for small noise values is larger as the probability for large noise values. And this is why if I observe such a red vector at my correlator outputs, it's more likely that a symbol 2 was transmitted as if a symbol 0 was transmitted. Yes. 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 So I mean, if you would break this down to the theoretical calculation of the error probability, like Dr. Mike Wolf's lecture, it turns out you need, again, the integral over the Gaussian distribution, and the further away your signal point is, the further you move towards the tail of this Gaussian distribution. The smaller will be your integral, the smaller will be the probability. Okay. So in our case, we could end up with a vector like this, and we would actually make the decision, well, what is reasonable now, how to make the decision. We just look at the largest value, because that's the most likely. Largest value. Most likely. So, and what was L2? Yeah, symbol 2 transmitted.
Sir,
Yes.
small doubt. Like the ln values that we have, is this like comparing to all mathematical calculations before? So is this P external or P internal? How can I correlate?
Oh, I'm afraid I didn't really understand.
Actually, I'm saying in the previous class we have seen LLRs, mathematical calculations, like 1/2 minus 1/2 pi. So just as a comparison, so the ones we have L1, L2, L3. So are these like P external we are using or P internal? I want to correlate with that. 1 minus Pj external by Pj external for the energy calculation we had previously.
Are you talking about this relationship up here?
Yeah, one more previous page, maybe on fifth slide, I guess. Yeah, this one. So
You are
like MJ. I'm comparing with this MJI dash, the last one.
Yes, yes.
So can I compare with this, the L1, L2, L3 that we found now?
Well, actually, if you are referring to this MJI, so let me go back to this one. So if we would deal with non-binary methods here, we would also get a vector for our EJIs. Would get for each EJI a vector containing 3 log likelihood ratios, and we would also get for the MJIs also vectors containing 3 values. So then everything becomes a bit more difficult.
Okay.
So we have to deal with vectors with all likelihood ratios as compared to the binary case where we only have to deal with scalar values.
Okay. Yeah, if we like do with that matrices, then it will be 3x3 matrix. Yes, like that.
Yes.
Okay. Yeah.
But
thanks, sir.
Actually, this is like beyond the scope of our lecture, and
Yeah.
this is also not used in 5G systems, for example. Just if you ever come to the point where some non-binary methods are used, keep in mind also there are definitions of things like log likelihood ratios. You just need to extend this idea slightly, and you will see this will turn out to give you some vectors containing log likelihood ratios. So not so important for us, but as a student asked, and it was a very good question, I wanted to answer this for you. Keep in mind, then you need to deal with vectors instead of scalars.
Wow, that's a good example.
Okay. Yes. So let's come back to, yes, another question. So here's the question. So what happens? So I'm not sure if I understood the question correctly, but there's one obvious question that could come up. What happens if the symbol is more close to the 0? Then you will see the 0 is more likely. The log likelihood ratio will be negative here. this one will be negative, and this one will be negative. So then, of course, we could also select from the absolute value the largest one, but in any case, this will tell us the 0 was more likely as the other value, or as all other values, basically. Maybe we include this as additional example, because otherwise I think this question could really come up with some points. Let's see. So this was the red example, purple example. Well, again, the 0 more likely than the 1. So this will be, yeah, a ratio less than 1, so a negative value. Also quite far away. So maybe minus 2.3. 0 compared with 2, it's very far away. The 0 way more likely as the 2, so minus 5.7 maybe. And also the distance to 3 comparable to 1, but also more likely, like a minus 2.5. You see, in this case, where we are more close to the 0, of course, all these log likelihood values will be less than 0. Well, and from this, we could actually conclude that 0 was the most likely. Most likely 0 transmitted. Well, then, depending on what we do with this log likelihood ratios, we might be able to get a benefit from this one. If we have here a very large value, we can say we are very safe that it is a 0. If we have here 3 fairly small values, this would be the case if we were somewhere here around the 0, then these values would be all in the same range. Then we could conclude from this value, well, it is a 0, but it's unsafe 0. So also in the values, we have some information on the reliability of the expression. Yes, yes. So let me repeat it. So here the question was, in the binary case, we just use the sign of the log likelihood ratio to get the information on the bit at the end. And yes, this is correct. Of course, at the end, we need to come up with an estimate. Is it a 0 bit or is it a 1 bit? So at the end, we need to do some thresholding. We need to come up with a value. And in the binary case, this can be done by using the sign. But of course, the same explanation holds. The larger the log likelihood ratios are, the more safe will be my sign decision in this case. Exactly. So you understood a lot. So here the student commented that this will depend on the Euclidean distance. And well, exactly that's it. So for example, if you had here an observation like here, so almost equal probable that a 1 was transmitted or that a 0 was transmitted. This will give you a very small log likelihood ratio because the probabilities are almost equal. So log likelihood ratio around 0, maybe plus 0.01. You would do your thresholding and say, okay, sign is plus, probably a +1 was transmitted. But due to the small value of the log likelihood ratio, you could still conclude it's a very unsafe decision. Whereas if you observe a value here, close to +1, likelihood probability for the 1 very large, you would get a very large log likelihood ratio. The sign would tell you again, probably a +1 was transmitted, but the large value of the log likelihood ratio will tell you it's very safe to conclude this. Yes, yes. Exactly, yes, yes. Yes, yes. So again, here, very smart observation from a student here. So for equal probability, we have the highest uncertainty. We could also describe this in terms of entropy and yeah, the most unsafe decision. In our non-binary case, this would be the case if you have observation around the 0 point here. So it could be a 0, a 1, a 2, or a 3, almost with equal probabilities. If we were exactly at the 0, we would get likelihood ratios of 0, 0, 0. So this means you don't know what to do. Yes, very good, very good. Okay, but as I said, just for you to keep in mind, there are also things going beyond the binary case. Okay, but I wanted to come to the lecture slides and explain you some stuff here with the example with numbers. So as a student last time was asking to put these lecture slides on the webpage, so they are on the lecture, the webpage. It's like lecture slides part 2 or something like this. There you will find them. Okay, so let's have a look at this example with numbers. The 7,4 Hamming code, as we were talking about the whole time, with its generator matrix, and we encode this 4 bits, 1, 1, 0, 1. We end up with the code word looking like this. We map it to plus minus square root EC, so the ones mapped to -1, so assuming again EC to be 1. The zeros mapped to +1, so this will be our transmitted vector, vector x. And then, of course, I modeled some noise. Assuming a signal to noise ratio of 5 dB, like a typical value, so on a logarithmic scale, converted to the linear scale. We also had this on the lecture notes, setting EC to 1. See, this will, of course, result in a larger EB. Think back when we started with the coding, so inserting redundant bits will reduce the energy per coded bit. So this is why the energy per coded bit is or must be less as the energy per bit. Okay, and with this energy per bit and the signal to noise ratio here, I could calculate the N0, like noise power spectral density. And from this, actually, the noise variance that I actually need to model the noise process. So if the signal to noise ratio became smaller, higher noise variance, this noise variance here will increase. Things will get worse. Okay, so using this noise variance, I generated a random vector following a Gaussian distribution with this variance. Here we get the noise samples. And this basically added to our transmitted message will be the received vector. So those are the values that are available at the receiver. And with these values, we need to come up with the best decision which code word was most likely transmitted. And we will actually see how this iterative decoder using the Tanner graph will work. Okay, here again, starting with the description, how we calculate the syndrome using the observation and basically here our parity check matrix and the Tanner graph as representation of this parity check matrix. We also talked about this one. So here we basically see which observations or which so-called bit nodes are linked to each check node. So you could say here for check node 1, we get the first, second, third of our information bits and the first parity bit. So number this 5 here is also linked to check node. So this is just the graphical representation of our parity check equations, actually. Okay, so then we basically have here one first example. If we have here some already decided bit values here, ones and zeros, we can actually calculate this check nodes or this syndrome bits, and we see syndrome different from 0. This here, the yellow one, cannot be a valid code word. Something's wrong here. And now the task is how to figure out what is wrong. And basically here we see again the whole process, the code word that we would like to transmit, mapped to plus and minus 1, the received values here after adding the noise, and with all the equations that we derived, the log likelihood ratios, so large values here, very likely to be a -1 here, whereas small values somehow unsafe. Actually wrong here. And also, instead of the log likelihood ratios, we could use the probabilities. We can calculate one out of the other, as described here above, just to give you a better feeling, how this log likelihood ratios translate into probabilities. So for example, here this value around 5 or 6 means also already a probability of like 99 point something %. So if we observe log likelihood ratios in this kind of number range, we are already quite safe about our decision. Okay, then here basically the example which we spoke a lot about it. How can we extract information from the neighboring observations for our observation of interest? So here the extrinsic information that we can extract for bit 3, bit node 3, over check node 2. Yes, and we already spoke enough about this one, so we should be able to understand this. Yeah, also, again, following the example with our numbers here, already explained this in detail. Here, how we calculated the probabilities. So from these 3 green guys, we can conclude with 88% probability, the third guy here must be a 1. Okay, then here, already the transition to the log likelihood ratios explained again, but I want to come back to our number example. Here, again, also straightforward, how the extrinsic information from all check nodes being linked to our bit node 3 comes together. At the end, forming the whole log likelihood ratio of our observation of our bit node 3. Well, we talk about this right away. We'll come to the example first. See? Okay. So just look at this example. So again, I modeled some received values here. It's noisy observations, some noise process, some transmitted values, and some actually mapped bit values. And now I wanted to see actually how the numbers evolve if we proceed as we learned it. See? In the next stage, I calculated here the log likelihood ratios of our observations, and again for you to illustrate the probabilities. So we have the noisy observations, we have the log likelihood ratios, and the probabilities. Again, here you see quite large values, log likelihood ratio of 9, so you already don't see the decimal points here anymore. So if you work with probabilities, you should work with higher precision. But that's one benefit of using the log likelihood ratios. You have like a reasonable number range. Okay, so in the sequel, we will forget about the probabilities. We will think more in log likelihood ratios. See what is new here. It's the same slide again. So, yes. Yes. So here was again the question about probability for a check node to be satisfied. But I will explain this again now looking at the lecture slides here. So of course we would start with bit node 1 and check node 1 if we want to treat all of them. So the first question is, what information can we gain on bit node 1 over check node 1 from all other bit nodes being linked to check node 1? So this is basically the first stage. And here I actually calculated these probabilities that we derived. Here, the probability that the sum of the green guys is 1 is 0.96. So basically, from the green observations here, from these 3 log likelihood ratios, I can conclude very likely the first guy must be a +1. Okay, so let's see how we can describe this. So with the probability 0.96, probability calculated in a log likelihood ratio, this corresponds with a log likelihood ratio of -3.1. So this is basically the extrinsic information that we can extract over check node 1 for our bit node 1. With this log likelihood ratio or with this probability, this guy will be a 1. Okay, just continuing this. Yeah, note, now here at this bit node 1, I have the -8.8 from the observation of bit node 1, and I have the -3.1 extrinsic information from these 3 green guys. This is basically just combining now what I know about my bit node 1. And now it's straightforward to continue. Next, I will ask, what can I conclude from check node 2 on bit node 1? We see check node 2 has no connection to bit node 1, so there's nothing I can basically gain on information using check node 2 because it's not connected. So here I get no information from check node 2. But I will get some information, extrinsic information, using check node 3 with, again, these 3 green guys linked to it. Again, asking the same question, what's the probability that the sum of the 3 green guys will be 1? This will be the probability that bit 1 must be a 1. So again, with the same questions, I can proceed here. So from these 3 green guys, I get the information, a log likelihood ratio of -8.9. So quite a very safe decision that the first guy is a 1-bit. So now notice we have gained information on this guy. So we information from the observation, we have some information over check node 1, we have some information over check node 3. See how this continues. So, and I do this, of course, for all the bit nodes. Story will continue in the same way. So for bit node 2, we have some information from the observation. We have some information because it's linked to check node 2 with some other bits. It's also linked to check node 1. It's also linked to check node 2 and also linked to check node 3. So this is basically how we would go along all the bit nodes and see what information can we get from the neighboring bits. Okay, are there questions so far? But I think this is straightforward. If you understood it so far, this is also easy, just doing this multiple times to get all the information that is available. So here was the information. If in the exam you have to show this kind of iterations, we will not have a task like this in the exam because it will be crazy to calculate these numbers, even though there are actually no calculators allowed in the exam. So I will come up with some more easy questions related to this, or some more feasible questions. Let's see. So I will give you some hints what I can ask related to this parity check codes. Maybe sometimes I also, if the math is too tricky or you just need numbers to come up, I sometimes also just ask understanding questions, like explain in your own words how the decoding works, or what's the meaning of this extrinsic log likelihood ratios in the decoder, or something like this. And you just need to write 2-3 sentences and explaining this. And from this, I see if you understood what is going on. So maybe some kind of this question. Yes, you don't have to solve these equations with numbers. Okay, so we end up with like information from the observation and like 3 parts for the 3 check nodes. So then basically the next question is, what is being sent back? So how do we continue with our iteration? So from check node or from bit node 1, of course, we also send back some information to check node 1 at the end. And this is the part which is a little bit difficult for understanding. We just send back the information from the observation, the information that we got from check node 2 and from check node 3. We don't send back the information that we received from check node 1 before. So the reason for this is because we want to use independent information during our iterations. And if we would transmit this 3.1 back up here to check node 1, we would basically reuse this information, because in the iteration before, we just received this value as a check node. So for the M11s, so basically the messages like going back to the check nodes, basically the message or the part that we received before from this identical check node is left out, which basically results in this -18 here. So it's this one and this one. No, it's just this one and this one. -8.8 plus -8.9. This will be this -18 and so on. So also here, when feeding back information to the check node from bit node 2, we just feed back all the values, just not the value that we received just before from this check node. So again, this would be a reuse of this information. So this is why we don't send this back, because this would be basically mean circling back and forth the same information. So basically, you tell me a message and I tell you back the same message. and one iteration later, you will tell me again the same message. So there's no point of feeding forward and back the same information that I received before. So this is why here just the extrinsic information that we received before from the same check node is not considered. So we continue doing this for all bit nodes being linked to our check node and getting this, this log likelihood ratios going up towards the check nodes. Okay, and that's basically already the whole story. Then we would combine again this log likelihood ratios M, as we described it here, and calculate again the extrinsic information. So from the M's, we could again calculate the following E values and so on. Follow this equation now with the updated M values, we would be able to calculate the new extrinsic information. Okay, so this is basically how this story works. Just want to put this in our slides. So the last step, because I wanted to explain this first. So come here to the step. Next step. Updating the MJI. MJI is again a sum over all J prime element AI, so all check nodes all bit nodes actually so AI is the union of bit nodes with a link to check node J. Just need to make sure that this goes correct. So let's take yes, so these are all check nodes. All check nodes that are linked to bit node I. Just J being different, J prime being different from J. Maybe it's good to make a drawing again here. Understand this. To have an example here. So we have all check nodes that are linked to one bit node. Consider this bit node here and assume here a couple of check nodes which are linked. So here we would I being example, and then this here would be A2. And the index J prime would be here like 1, 3, and if you are interested in MJ1, let's go with the example, EG, M, say 2. So we would be interested in this one here. So what we use is basically E J prime I plus the Ri. So we basically use Ri. So what we know from the observation, we use the five, 2. We use the E1, 2. And basically that's the information going up here. And this is why we don't use the E32. Would be reuse already existing information. So this would be the red guy, the M, J. So this is basically the message going up to the check node. So what can we learn from our previous observations, from our extrinsic information, then to update the values at our check nodes? So updating check nodes. And with this, we are basically done. Summary. Also find this on the lecture slide. So we need to calculate priori LLRs, so from our observations. We call those Ri. Then first iteration. Message to check nodes. mji is equal to our Ri. This is all we have. It's the first observation. We just see our noisy received values and we have to do something with them. Then we use the relationship at the check nodes to calculate this extrinsic information. Calculate messages. To the bit nodes. So EJI. And with this information coming from the check nodes back to the bit nodes, we can calculate the bit node LLR. So this was simply the a priori LLR plus, well, again, the sum of our EJIs. And of course, we could already come to a decision. So we could do a thresholding. And check for zero syndrome. If we get the syndrome zero, we are done. We know now it's a valid code word. Let's decide for this one. If not, we would basically continue. Update. MJI. And 7 with the MJI, so the messages to the check node, we would be able to update the extrinsic information, basically go to, so then we would calculate again the EJIs and so on, until we end up with a valid code word. Okay, so not very easy, I have to admit, but I think it's from the principle, it's not too difficult to understand. It's basically feeding back and forth information in this tenor graph using the fact that the bits are somehow linked together along the check nodes and exploiting this information to gain additional information on our observations. And this in an iterative way, thus improving our information. Okay, So if there are no questions, we basically can continue by thinking about what can be good or bad in a parity check matrix. There are obviously matrices that are better suited for this kind of decoding method as other ones. We will see our 7,4 Hamming code will not have a very good parity check matrix to do this kind of decoding, but we will try to understand why it is like this. Yes. Yes, so here's the question what this MJI is actually called. I don't really have a specific name for this, but as I look at my diagram now, it becomes even for me more clear. So obviously the MJI is the extrinsic information on check node 3 here in this case that we can get from using the other check nodes that are not linked to, or yeah, from basically the observations on the other check node, we can get information on this desired check node. So I would call it the extrinsic information for check node 3 that we can get from using the other check nodes. And the fact that they are linked over bit node 2. See? The check nodes are linked over bit node 2. So this means I can extract some information from the other check nodes, extrinsic information on check node 3. So it's basically as before, just the other way around. Very good question. Yes. Yes, so even I have difficulties understanding this MJI, but actually this is a very important drawing. So maybe I should include a similar drawing also in the lecture slides to make this more clear what is going on in this MJIs. Okay. So let's come to one further point. Thinking about good or bad parity check matrices. So what can be good or bad parity check matrices? Let's look at the effect. Cycles in a Tanner graph. Let's use our typical one, like from the 7,4 code. Example here, we sky 2, 3. Seven sky. I want to draw this once more. So assume we are interested in the first bit. So we would ask in the first iteration, what can we get from the linked bits on information for our desired bit? This is like one typical question. think we need this one also. And the last one. And so on. We don't need to draw. So looking at the first guy, here we get actually independent information. Independent information in the first iteration. And now notice in this Tanner graph, we have a so-called cycle. So this means, okay, it could be, so I pass up my information here. In the next, and then down to bit node 1. In the next iteration, I will move forward again, this information up to this guy, which will actually come back along this way. So here basically we see in the second iteration, we will have we will use information that is already been used before. So just imagine the first bit node, or let's say this second bit node here, being a very unsafe, very noisy observation. You see, in one iteration, we will use it as information to determine bit node 1. And one iteration later, this will actually influence back again our bit node 2. So the influence of the bad observation here, 2 iterations later, it will come back to the bad iteration. So the system will basically influence or limit itself by circling back information. So basically here, the independence gets lost. Independence is lost. This basically results in a degradation of decoding performance or degradation of bit error rate. Achievable this way. Bit error rate is limited, reduced. Actually, the bit error rate is, let's stick with the limited. So this would be a so-called cycle of length 4 in our case. So 1, 2, 3, 4. I'm back at the origin. Cycle 4. Just to give you an idea how this could look like. Simulate this. SNR, signal to noise ratio. Then it could be that it starts very well. Then somehow it starts limiting. Example here. Or as if we had cycle. Yeah, it's not so good case. This would be the case loop cycle. If we don't have a cycle, the bit error rate will go like straight down, better and better. Whereas in the case we have the cycle, due to this reuse of information, we will be limited by the achievable bit error rate. So this will turn towards such a convergence towards a certain bit error rate where we just cannot get better because we again reuse bad information that we already have and cannot get better because we are again and again use this bad information that we have. So this is why the performance is limited if we have this kind of cycles. So cycles are performance limiting if we talk about these LDPC codes. And this is also the reason why our 7,4 Hamming code will not be a very good LDPC code. Because here, see, we have such a cycle. And if you look at the Tenor graph in more detail, you will find even more cycles of length 4 in this Tenor. Yes. So here's the question how we determine the length of the cycle. It's basically the number of paths until I get back to the origin. Like 1, 2, 3, 4. But I also want to give you another idea how to determine this so-called support tree. So e.g., so in the lecture slides, I have the support tree for bit node 1. Maybe this also answers your question a bit further. So that's also a method how to identify the cycles and how to identify the length of the cycles. So to get this support tree, I will basically just start with bit node 1 and looking at the tenor graph where it has connections to. I look at bit node 1, it's connected to check node 1, check node 3. So it's connected to check node 1, check node 3. Then from check node 1, I look to which bit nodes do I have a link from check node 1. So if I do this, I will see it's bit node 2, 3, and 5. So still following the example of our 7,4 Hamming code. And from check node 3, I have connections to bit node 2, 4, and 7. And I could continue this way, again asking to which check nodes do I have connections from bit node 2. This could go further here, so on. And now you will see I get a cycle if I have here 2 times the same node. So I see from bit node 2 over check node 1, over bit node 1, over check node 3, I end up again at bit node 2. So in this tree, I can easily identify cycles So here we have a cycle of length 4. Over bit node 2. Actually here also just coming up with some definitions. So this would be the support tree. Level 2. So the depth of the tree is 2. And with the support tree of level 2, I can identify cycles of length 4. Support tree level 3, I could find cycles of length 6. Support tree level 2. Level 3. To identify cycles six. So here's the question. So the larger the number of cycles, the better will be the bit error rate performance. I think you mean the correct thing. So the larger, the smallest cycle that appears, the better will be the bit error rate. So if we look at our tenor diagram, we could have cycles of length 4, cycles of length 6, maybe also cycles of length 8. So we can have many different cycles, but the ones that will limit my bit error performance will be the small cycles. So we would like to get parity check matrices that result in Tenor graphs avoiding the small cycles. So for example, one task when coming up with good matrices for LDPC codes, one task is to find good matrices which do not contain cycles of length 4 or of length 6. This is a design challenge when thinking about matrices for parity check codes. So wait, let me show you this one. Oh, time is running out. So we will continue there next time. So of course, we can also see how these cycles reflect in the parity check matrix, because the Tenor graph actually results from the parity check matrix, and I will see that the cycle of length 4 has a certain pattern in the parity check matrix. So in order to get a good parity check matrix, I would like to find a parity check matrix which has a Tenor graph that does not contain the cycles of length 4. Because with the cycle of length 4, already after the second iteration, I'm reusing information. Whereas if I had a cycle of length 6, I could already have 3 iterations, where in each iteration I get independent information. Just after the third iteration, I would start reusing stuff that I already used before. So I would like to have Tenor graphs without short cycles. Short cycles. So of course you could say now I would like Tenor graphs without any cycles. You could also say let's try this. But there you would see that this kind of parity check matrices will result in codes with only low minimum Hamming distances. So that's one other point that we have to consider when looking or when choosing certain parity check matrices. So we basically have 2 constraints. We don't want the short cycles, but on the other hand, we want large minimum Hamming distances. So those are the 2 optimization constraints which will at the end result in certain structured matrices. Okay, but we will continue there next time. So for today, just again, think about the cycles and this idea of how information is reused and why it is not good to reuse information. That's the main message for today. Okay. So are there further questions? Then we will continue there on Thursday. And then that's it for today. Thank you for your attention and have a nice afternoon. See you on Thursday. Goodbye.